For the first time ever, scientists may have captured the birth of a supermassive black hole. Not inside a star, not at the core of a galaxy, but in the violent heart of a cosmic collision. In the Infinity Galaxy, Webb has revealed a black hole forming between two galactic centers, like it emerged from nowhere. If this holds up, it could rewrite the playbook of how giant black holes first appeared in our universe. The shocking part? The data so far actually supports it. But what does it really mean to watch a supermassive black hole being born? Could this discovery change everything we thought we knew about the universe? Let us know your thoughts in the comments below. How could something as extreme as a black hole with billions of times the sun's mass appear when the universe was still in its infancy? Less than 1 billion years after the Big Bang, astronomers see quasars powered by monsters that shouldn't exist yet. Growing to that size takes time, and there just shouldn't have been enough of it. So the puzzle is not only about these objects themselves, but about whether the early universe even allowed for such rapid growth. To untangle this, scientists put forward two main ideas. The first is often called the light seed model. It suggests you begin with black holes that form out of giant stars when they collapse at the end of their lives. These seeds might start with maybe 100 times the mass of our Sun. The other proposal is the heavy seed model, which skips the star stage entirely. In this case, vast clouds of pristine gas collapse directly under gravity's pull, bypassing the creation of stars. The result is a black hole that begins already in the range of 100,000 solar masses, a massive head start. Think of it this way. A light seed is like planting a tiny sprout in the ground. With time, sunlight, and nutrients, the sprout can grow into a large tree. But that kind of transformation takes patience and steady growth. A heavy seed, on the other hand, is like having a tree delivered that is already fully grown. Instead of waiting centuries, the massive structure is present right from the start. The direct collapse scenario seems efficient on paper, but proving it has been another matter entirely. Computer simulations have given some reason to believe that heavy seeds could form under very strict conditions. The gas has to stay hot enough not to fragment into countless stars while still piling up fast enough to trigger collapse. Only a small fraction of early galaxies might have had these conditions, which explains why evidence has been difficult to find. Yet the very existence of enormous black holes in the universe's first billion years seems to demand some mechanism like this. What makes this question more than just academic is its impact on the big picture of cosmic growth. Black holes don't develop in isolation. Their gravity helps shape galaxies. Their radiation influences nearby gas, and their mergers carve out some of the most energetic events in the cosmos. If heavy seeds were common, then the blueprint for how galaxies assembled looks very different from a picture built only on light seeds. The challenge is that the universe has done a good job hiding its earliest black holes from direct view. For years, astronomers worked with theory and simulations, but lacked a clear case to point to. The early giants we can see are already so massive that by the time their light reaches us, we only observe the end result, not their beginning. That gap is why the hunt for a real-world example has been so intense. And now, with new instruments, there might finally be a system that doesn't just theorize heavy seeds, but shows one in action. The strange behavior of a galaxy that looks like a cosmic infinity symbol is forcing researchers to reconsider what's possible. What could be stranger than seeing two galaxies smashed together? Finding a black hole sitting in a spot where no black hole should be. That's exactly what astronomers noticed inside a peculiar system now nicknamed the Infinity Galaxy. At first glance, its structure catches the eye because two disk galaxies are colliding head-on, creating a luminous shape that looks like a stretched-out figure 8. The arcs of stars and gas loop around in giant rings, almost like ripples frozen in space. But nestled in the middle of that chaos was a discovery that didn't fit the expected pattern at all. In cases like this, each galaxy should carry its own central black hole. When they merge, you would anticipate finding a pair of black holes locked near the cores of their parent galaxies, slowly spiraling together. But here, researchers saw not 2, but 3 black holes. The extra one wasn't neatly parked inside a galactic nucleus. Instead, it floated between the 2 stellar disks, almost suspended in the gas-rich tidal bridge. That placement is so unusual that it immediately raised the suspicion that something new might be happening. The first hints came from sharp web images, which showed the unusual ringed collision and revealed bright regions that caught attention. To test whether one of those bright points really was a black hole, and not just a knot of star formation, astronomers gathered more observations. The Keck Observatory added precise data on how stars and gas moved. Chandra X-ray Observatory then picked up emissions that only an active black hole would produce, and the Very Large Array Radio Telescope confirmed persistent radio signals from the same location. Piece by piece, the evidence built a consistent picture. A black hole is glowing and feeding, but it isn't anchored where the centers of the colliding galaxies should be. To picture this, imagine a giant gas cloud stretched between galaxies, flared and stirred by violent gravitational forces. Now imagine inside that gas cloud a black hole actively pulling matter inward, yet not tied to either galactic center. It's a strange image because everything we know about these objects tells us they settle at the core, not free-floating in a bridge of gas. That sense of dislocation is what makes the Infinity Galaxy such an unusual case study. Naturally, scientists asked if there could be simpler explanations. One idea was that it might be a runaway black hole, maybe one ejected from a galactic collision, now drifting through the intergalactic medium. Another option was a tiny, faint third galaxy, hidden in the glare, that happened to host its own black hole. Both explanations seemed possible at first, and without careful testing, they couldn't be ruled out. The debate gave the system an extra sense of mystery because whichever answer turned out true would still challenge expectations. That meant researchers needed a way to discriminate between these scenarios, to figure out if this black hole truly formed where it now sits. The solution came from studying the movement of the black hole compared to the swirling gas around it, and that is where the story took a crucial turn. How do you prove a black hole was actually born in the very gas cloud where you now see it? That's the challenge astronomers faced in the Infinity Galaxy. Spotting the black hole was one thing, but establishing whether it truly formed on site required a kind of fingerprint test. The key was motion. If the black hole shared the same movement as the gas around it, then that would argue it belongs there. If it didn't, then other scenarios, like a runaway black hole that drifted in from somewhere else, would become more likely. The method used is known as a velocity test. It involves measuring how fast the gas near the black hole is moving and comparing it to the velocity signature of the black hole itself. Webb provided the spectra of ionized gas, the stretched or compressed fingerprints of light that reveal motion through the Doppler effect. In simple terms, astronomers could track whether the gas was moving toward us or away from us, and at what speed. Meanwhile, the black hole was marked by its energetic emissions that could be traced in X-ray and radio data. If the two didn't match, the story would unravel. The task was not easy. Webb data had to be carefully parsed to map out the gas cloud's velocity distribution, which isn't uniform but spread across a range as gas flows and collides. On the other hand, the black hole's signature had to be pinned down across multiple wavelengths. By overlaying these measurements, astronomers could see how well the two matched. If the black hole was out of step, it would show up as a clear offset. Instead, the result landed squarely in the middle of the velocity spread of the gas. It was not racing past, not lagging behind, not standing apart at all. In fact, the match was so precise that it suggested the black hole was anchored in the same gravitational environment as the gas cloud itself. A good way to picture this is like watching a crowd of people walking down a street. If someone is just passing through, they stride at a different pace. If they belong in that group, they move exactly in rhythm. This black hole was keeping perfect time with its neighbours. The Infinity Galaxy may mark the first time we have direct observational hints of a supermassive black hole born straight from collapsing gas. If this finding holds, it shifts the story of the early universe because it shows growth did not always begin from tiny stellar remnants. Instead, entire gas reservoirs may have skipped the slow build-up and produced giants in one leap. That means the young cosmos created black holes faster and more efficiently than we imagined. So next time you hear about galaxies colliding, remember they may not just merge stars, but also forge new cosmic giants. That's it for today's episode. Thanks so much for watching. If you enjoyed it, don't forget to hit that like button and subscribe so you don't miss what's coming next. We've got plenty more mysteries to uncover together. See you in the next one.